Good morning to all of you. I hope you liked the last two lectures on polar coordinates. So today we are going to do some problems. So it is a problem session and I have selected some 5 problems. 2 problems I have taken which are solved in Klebner. Other 3 I have taken from a very well-known book, Dynamics by Merriam. Okay. So let me quickly recapitulate what we have learned in our last 2 polar coordinates lectures. Now in polar coordinates, what we have seen that any curvilinear motion basically can be broken up into 2 parts. One is a linear motion which is going away from the center, and that we take up by r cap direction. The other is the angular motion, basically angular motion, and that is theta cap direction. In the linear motion, we have to calculate r dot, r double dot. In the angular part, we have to calculate theta dot, theta double dot. Now, moment you know all these 6 quantities, you can calculate velocity vector and the acceleration vector. The velocity vector is r dot r cap plus r theta dot theta cap. Acceleration vector is r dot minus r theta dot square r cap plus 2 r dot theta dot plus r theta double dot theta cap. So these 2 formulas you have to remember. Okay. So let us come to the first problem, that is example 1.16 of Klebner. Let me read out the problem first. Now the problem says a bead moves outward with constant speed u along the spoke of a wheel. It is moving outward along the spoke of a wheel with constant speed u. It starts from the center at time t is equal to 0. So at time t is equal to 0, r is equal to 0. The angular position of the spoke is given by theta is equal to omega t. Theta is equal to omega t is the angular position of the spoke, where omega is constant. Find the velocity and acceleration. So we have to find out the velocity and acceleration of the bead. Okay. Now this kind of problem, basically a very common type of problem, and often you will see this problem in the exams also. You may get similar kind of problems, that something is rotating like merry-go-round or anything, and a particle, either it is going away from the center or coming towards the center. We have to find out its velocity and acceleration. So it is a very common problem, interesting problem. Now before we proceed, the first thing that we do is choose a coordinate system. So let us take this this is your x-axis and this is your y-axis. Alright. And here, since the particle, and in the particle we put the r cap and theta cap. So let us take, this is your r cap away, and perpendicular to it is theta cap in the direction of increasing theta. Okay. So now we have to calculate velocity. But before we calculate velocity and acceleration, it is always easier if we calculate all these 6 quantities before. Okay. So let me quickly write r dot, r double dot, theta dot, theta double dot. R is given by, now what is r? Since it is going with a uniform speed u, r will be u into t with time. R dot will be u, R double dot 0, theta is given by omega t, theta dot omega, theta double dot 0. The moment you finish this table, it is very easy and you don't make any algebra or your silly mistakes. Okay, so let us calculate velocity vector. So V is equal to R dot R cap plus R theta dot theta cap. R dot is U R cap plus R theta dot, R is ut, theta dot is omega and theta cap. That's all. This is your velocity vector. So you can write it like this. Alright? Velocity vector. Then we calculate acceleration. Acceleration is just this formula, R double dot minus R theta dot square R cap plus 2R dot theta dot plus R theta double dot theta cap. Now quickly write this. This is equal to R double dot is 0. So minus R is ut, theta dot square is omega square, R cap plus, again as you see here, R theta double dot is 0. So it is 2, R dot is u and theta dot is omega theta cap. So this is basically your acceleration vector. You can make a box over here. And the question asks you to find out the magnitude, that also you know how to do it. So this is your acceleration and velocity, the vectors. Good. So the question, whatever the question is asking, that is done. But let us do something more. What we do here is that we are interested to find out the trajectory of this particle. Now as you see, this particle is going outward and at the same time this wheel is rotating. So as you see that it is making a spiral motion. Okay, it is making a spiral motion. Now if I want to plot the trajectory, how to plot it? What should I calculate? I have to calculate R basically. R means the position vector R vector. Alright. So I have to calculate the position vector R from the origin. So if I calculate that, I can plot the trajectory. So let us quickly write R vector is R cap. And what is R? R is ut and R cap, basically in order to plot it in the xy coordinate, I have to write it in terms of I cap and j cap. So R cap, as you know, we have studied, it is I cap cos theta, I cap cos theta. Now theta, as we know, is omega t. So I write omega t plus j cap sin theta, that is sin omega t. Now, moment you write in the term of omega t and t, now what you do, you take any values of t from 0 to, whatever values you want to take. Now 0, as you see, it is 0 basically. So from there it will start. And the moment you take values from 0 to whatever values, you will be getting the position vector. Now, let us plot it. So if we plot the position vector, so let me do it like this. This is your x-axis and this is your y-axis. So if I plot it roughly, so it will be something like this. Something like this, alright? Okay, now here, if I plot or if I want to know the velocity vector, let me draw that. So this is my point of origin, and here I draw the velocity vector. Suppose say this is my r cap direction, this is from O, any point I take. So basically this is my r cap vector, and perpendicular to that is my theta cap vector. Alright. Now along this direction I have V of r. Along this direction I have V of theta, and this direction basically, if I add both of them vectorially, this is the direction of V, the vector V. Alright. Let us take some point over here. So let me okay. So let me good. So this is basically your r cap direction, and this is basically your perpendicular to that is your theta cap direction, and your velocity vector is basically this one. This is your velocity vector, that is your v. So as you can see that every point I can find out the velocity, and this is the trajectory of the particle. I hope this is clear to you. Okay, now here there is a very important question. Listen carefully. The question is that, this is what in the book also it is given. If you see that book, this diagram is given. But let us go something beyond. What is that we learn from this picture or diagram? One important question comes many a times, and the question is that as we see that, suppose say this particle is moving a spiral path, or this is moving like this. Now at every point what we see that our r cap, theta cap or polar coordinates is basically rotating with the particle or moving with the particle. Here it is also rotating with the particle, here it is moving with the particle. So this particular polar coordinates, sometimes it is compared with a rotating frame. Because suppose if I fix a rotating frame here, alright, and that rotating frame is rotating with this wheel, okay, so it is a rotating frame, so at that time the axis x prime y prime is rotating with the particular wheel, or it is a rotating frame. Now sometimes people feel or people compare or ask this question that if this polar system or polar coordinates similar to or equivalent to a rotating coordinate system. Do you understand this? Okay. Another thing that happens is in the rotating frame, when we calculate the acceleration in the rotating frame, that we will do it much later in the chapter of non-inertial frame. So in a rotating frame, when we calculate the acceleration, expression for acceleration, that expression interestingly have some terms which are very similar to the acceleration terms over here. Like there, you also get this term 2r dot theta dot, maybe with sign different, but you get this term 2r dot theta dot. You also get this term r theta dot square. So there, this term is mentioned as Coriolis acceleration. In fact, here also it is mentioned as Coriolis acceleration, which I didn't want to tell you in the last lecture. This term, there it is known as centrifugal term, this term, from where you get the centrifugal force. Okay, so basically this term and this term are also in that acceleration. So in what way they are similar, in what way they are different, that is the question. But anyway, that is a very detailed discussion, and I thought about it and I planned to give a little bit detailed lecture on that. But for the time being, in this question what we learned is that this polar coordinate, which is your r cap theta cap, though it is moving with the particle, but this system of polar coordinates with xy coordinate system is a inertial frame of reference. Alright? It is an inertial frame of reference. This is not rotating frame, is a non-inertial frame of reference. Now as you can see, in a inertial frame of reference, we can plot exactly the path of the particle. Exactly the path of the particle is known, and at every point we can calculate the Vr and V theta and the V. So this system is totally a inertial system, whereas this is not, because in a non-inertial rotating frame, suppose this frame is rotating with angular velocity omega, same velocity as this wheel, then in that frame we will see that this particular particle is going away from the center. Alright? So we will not see the actual path, but here in the polar coordinates, as we see that we see the actual real path of the particle along with its velocity or acceleration, whatever. So this is the main difference, and till now this much. Later on, if you are interested, I will make that lecture and you can listen to it in detail. The comparison between the polar coordinates and the rotating frame. Good. Now let us come to the question number 2. Question number 2 is example 1.17 of Kepler. It is also a very interesting question. Question says a particle moves with theta dot is equal to omega is equal to constant. Theta dot is equal to omega is equal to constant. And r is r0 e to the power of beta t, where r0 and beta are constant. R0 and beta are constant. Find that value of beta for which the particle moves with ar is equal to 0. For what value of beta ar is equal to 0. Now, this is also again a very, very interesting problem. The problem is interesting because as we see that the radius or r is exponentially increasing with time. At the same time, if I calculate the radial velocity r dot, that is also exponentially increasing with time. So the question is, if the velocity is increasing exponentially with time in the radial direction, why the radial acceleration, or how come it be 0? But let us see that. So let us calculate AR. So AR is equal to AR, this is the AR basically, alright, R double dot minus R theta dot square. This is the AR, expression for AR. And how much is this? R double dot is R0 and e to the power of beta t. So basically twice we have to differentiate. So you will get beta square, alright, then e to the power of beta t minus r is again r0 e to the power of beta t, and theta dot square, that is omega square. So I can take common, that is your r0 e to the power of beta t common. So you get beta square minus omega square. So this becomes your AR. That is radial part of the acceleration is this. Now it says for what value of beta AR is equal to 0. So put that is equal to 0. Okay. So this term can become 0 when beta is equal to plus minus omega. So this is my answer. Now, this is very interesting. So AR is equal to 0 when beta is equal to plus minus omega. Now it is very, very interesting because the radial velocity is exponentially increasing with time, but radial acceleration becomes 0 at this particular value. What does this question teach us? Why does it happen like this? That is the question. Think about it. Why does it happen? Now, the explanation is, as we have read, that this particular acceleration term, that is your radial acceleration, consists of two terms. Alright? Two terms. So one is your r double dot terms, which I make it in red, and another is your r, okay, let me do this, this is the second term, r theta dot square. So that is the first term and the second term. Now, r double dot term is basically, again as we discussed there, r double dot term is radially outward. So, if the radius or r is changing, we are getting r double dot, that is radial acceleration, which is linear acceleration from there. So obviously, this term we will get. But r theta dot square, that also you are getting. R theta dot square, from where is this term coming from? R theta dot square. As you can see this diagram, any curvilinear motion, you can see this diagram. That second term is coming because as you see that in a curvilinear motion, the direction of the tangential velocity, you can say, is always changing. And the direction of the tangential velocity, we can break it into two components. One is radially outward and one is in the theta cap direction. Alright? So, because of the theta cap direction, the component which is along the theta cap direction, which is your v theta, when we differentiate and we get the acceleration. So, the second term, that is r theta dot square, which is your centripetal term, we are getting because the direction of v theta is changing. Alright? Now, direction of VR is also changing. Because of that, we are getting some other term. That comes from the second part actually. Other part, that is theta cap part. But in the radial part, the second part is coming because of the changing v theta. That is theta cap. Theta cap is changing. And that is why you are getting the second term. Now, and that acceleration is towards the center. So, one acceleration is away. That is because of changing of r away from the center, and because of changing direction of this v theta or theta cap, so other acceleration is towards the center, and at this point both of them cancel each other. So though the particle is going radially out with an exponentially increasing radius, but the acceleration radial component, the final acceleration component in the radial direction, you get 0 because of this centripetal acceleration. So it is a very, very interesting problem. So you get a feel of it, basically, both these terms. So in polar coordinates, you cannot calculate from the acceleration components, like what we can write, that AR, basically AR is a function of time here, AR dt, from there you cannot calculate V of R. So this is not true. It is true in the case of Cartesian coordinate, but in polar coordinates, since the theta cap and r cap, they are changing with time, so component wise, from the components you cannot calculate the VR. So AR dt is not equal to VR. This is an important thing that we learn from this problem. Okay? Let me come to the third question here. Third question is taken from Miriam. Okay. So let me discuss this problem or read out this problem. A tracking radar. So this is the radar over here. So let me write radar. All right. A tracking radar lies in the vertical plane of the path of a rocket. So this is a rocket. A radar lies on the vertical plane of the path of a rocket. So rocket is flying like this, which is coasting unpowered flight above the atmosphere. So it is not powered. So above the atmosphere it is going. For that instant, it is given at the time t, for some instant, theta is equal to 30 degree. This is theta. Now mind it, theta here is measured from the y-axis. For the instant, theta is equal to 30 degree. Theta dot is given to us, r is given to us, and r dot is given to us. All these given quantities are given. Then it says the acceleration of the rocket is due only to gravitational attraction. The acceleration of the rocket is due only to gravitational attraction, and for this particular altitude, g is equal to 9.20 meter per second square vertically down. So that is what I have shown here in this figure, that it is having an acceleration. This is your acceleration, alright? This is your acceleration. And acceleration is downward. So acceleration vector is given to you. Then they are asking velocity. What is velocity? What is r double dot and theta double dot? These are the things you can calculate. Okay. So how to do it? How to go about it? Here what you have to see, that acceleration vector is downward and its magnitude is given. So you get the acceleration vector that is given to you. Okay? Now what you can do, this is your theta, this is also your theta. As you can see, this theta is increasing from y direction. So this is your theta cap is basically in this direction. And this is your r cap. Alright? Now, this acceleration vector is given to you. The first thing, we will not solve this problem totally because a lot of calculations are there. The first point that you have to remember, there are 2 points. The first point that you have to remember, the problem is given in 30 degree, 0.80 degree per second. All these you have to change to radian. So change to radian by multiplying with pi by 180 degree. Pi by 180. moment you multiply by pi by 180, it will change to radian. So that is the first point. Second point is, your acceleration vector is now given to you. So what I can do, I can take component of this vector along the two directions. So let me take the component of this vector along the two directions. That means along this direction and along theta cap direction. So if I take that component, this is your AR, alright? This is your AR. So I write AR, what is your AR? G cos theta. But G cos theta is in the negative R cap direction. So I must write minus G cos theta is equal to write the expression for AR. AR is R double dot minus R theta dot square minus, this is G cos theta, this component is minus of from the opposite direction, so minus G cos theta is R double dot minus R theta dot square. Radial component, that is what we know. What is the theta component? A theta is basically, A theta is G sin theta. G sin theta is equal to 2R dot theta dot plus R theta double dot. Now you will see from these two equations, most of the quantities, like you have to calculate R double dot. So your theta dot is given to you, R is given to you, so you can calculate basically your R double dot. Exactly the same way, once you know the R double dot, so that is known, theta double dot also you can calculate from this equation, because R dot and theta dot is known to you. So here as we see that the acceleration, that it is falling, the rocket is freely falling. So the gravity, the acceleration vector is basically G. Okay, and from there, it is given, I can calculate the radial component and the theta component, and that I can equate with these two. That is your radial component of expression and the theta component, and from there I can calculate. Good. Now we go to the next problem. This is also from medium. Alright. Now this problem I have given to you in your notes. So it is basically solved in your notes. But it is a good problem where we calculate, from the acceleration vector we calculate the reverse wave. Now another problem. This is problem number 2, chapter 2, 140 of medium. Let me read the problem. Problem says the slotted arm OA. So there are two arms. One is longer arm and one is shorter arm. Okay. Now, when this longer arm is basically moving, it is given an theta, some oscillation. That oscillation is maximum is 2 theta 0. Theta is given by theta 0 sine 2 pi t by tau, and tau is the time period of oscillation, complete oscillation, time period of complete oscillation. Now as this is moving, this larger block, there is a slot over here. Now this particular rod that you see, here there is a pin. This pin is basically fixed in this slot. So as this is moving from here to here, this pin is basically moving from, it is doing a to and fro motion. So is this problem clear to you? As it is moving like this is moving like this simple harmonic motion. So the question is, they have asked, find out the acceleration at two different times, that is tau by 4 and tau by 2. Now again, it's a lot of calculations are there, algebra is there, but how to do it, how to approach this problem basically? Would you like to think about it for a minute? How to start this problem, or how to go ahead with this problem, or what is the key point in this problem? See here, this kind of problem we call as constrained motion. Okay, constrained motion, alright. Here as you see, this is basically your R. This is basically your R, because this is fixed over here. This is your R. This arm is your B. So my all calculations like R dot, R double dot and everything is basically with respect to this rod, the slotted rod. This is my R and this is my theta, the way it is moving. So with respect to this rod only I have to do it, not with respect to this one. So this is my main rod and this is your R. So this is your R which is changing. Now in these kinds of problems you will see how to go about it, because as you see theta is given to you, R is not given, but it is a constrained motion. That means two things are basically, two bodies are fixed together and they are moving in a constrained manner, and obviously there is a relation between them. So we can find out that relation. So that is the key, and that we have to find out that relation. Otherwise other things are just mechanically you can do it. So as you see, this is a triangle. So if you draw this triangle over here, so it is something like this. Now, if you know that this length is your R, here this is your theta, this length is B, this length is also B. Now as you see, this is simplified. This is B, this is also B. So what should be this angle? This is isosceles triangle. So this angle is also theta. Now I can find the relation between R and theta. How? By the sine rule that you have studied in trigonometry, sine rule. This angle, what will be this angle? This angle is 180 degree, that is pi minus 2 theta. So this is pi minus 2 theta. Pi minus 2 theta. Pi is total 180 degree minus 2 theta. So you can write this R by sine of pi minus 2 theta is equal to B by sine theta. So what sine pi minus 2 theta is? Sine theta, sine 2 theta. So 2 sine theta cos theta, sine theta will cancel. So R is equal to 2B cos theta. Okay. So now as you see, you have got the value of R. Once you got the value of R, then you can find R dot, you can find R double dot, and there you will get, when you differentiate cos theta, you will get a theta dot term basically. So theta dot basically you can calculate from here, and finally that everything will come in terms of t. Then you place t is equal to tau by 2, and I would like to give you the answers for this so that you can calculate. The answers are, so let me write the answers over here. Answers. A is equal to, for the first case, that is t is equal to tau by 4, the answer is 8 pi square theta 0, 8 pi square theta 0 b by tau square. And for the second case, when t is equal to tau by 2, for this case a is equal to minus of ar actually, and that is a theta component is 0, 16 pi square theta 0 square b by tau square. So this will be minus. I have written minus over here. Basically a is minus of this. Alright. So these are the answers you can try. Okay. So this is the important problem, and you will get many different kinds of problem with this constrained motion. The next problem is similar but little bit different. Let us come to the next problem, again by Miriam. Miriam has a good number of problems, and the book is Engineering Dynamics or Dynamics by Miriam. It is a quite an old book, but still it is very nice. Very nice and colorful problems are there in that book. Now let us see this problem. Here what happens, let me read out the problem first. This is problem number 2, 140. The last one I have not written, but I don't have the answers of this question actually. This question. The hydraulic cylinder gives pin A. So let me write A over here. Give pin A constant velocity. So this pin is a constant velocity. V is equal to 2 meter per second. So it is given V is equal to 2 meters. This is V. V is equal to 2 meter per second, which is constant. Good. So hydraulic cylinder gives pin A constant velocity. V is equal to 2 meter per second. Along its axis for an interval of motion. Along its axis for an interval of motion, and in turn causes the slotted arm to rotate about O. So this slotted arm is rotating about O. So this is giving a velocity to it, a constant velocity in this direction for which this is rotating. Determine the values of r dot, r double dot, theta double dot, when theta is equal to 30 degrees. So basically they want us to calculate the numerical values. Exactly numerical values when theta is equal to 30 degrees. So what is the numerical value of r dot, r double dot, theta double dot? So how will you do it? Other than the concept which I told you there, constrained motion, here also we have to do it anyway. But there is one more very important concept over here, which was basically in that problem. Now, in a little bit different way it is coming over here. See, when you get an exam, in the examination, when you get a question, it is basically a permutation combination of different problems, alright, a mixing up. And that is why if you are thorough with the questions that are discussed in the class, as well as all the assignments, okay, then it is very easy for you to solve a question in the exam. Sometime later, I will tell you, or maybe sometime later, that how you can study so that you can remember all the problems fresh in your exam hall, and that will help you to solve the problems. So that is one thing that you have to do anyway. That is finding out relations between r and theta and everything. But there is something else. What is that? Something else that you have to find out. Something else is that you have to find out, and that is a very important thing, that this velocity is in a straight line. It is not having any circular motion. It is in a straight line. And this velocity is constant. Alright? Whenever you see this constant, the word constant, I forgot to write it right at the beginning. Whenever you see this word constant anywhere, that means its higher order derivative with respect to time is 0. So velocity is constant, that means acceleration in this direction is 0. And it is moving in a straight line, so obviously not like the case before. So it is moving in a straight line. Acceleration 0 means the component of the acceleration in the two directions will be 0. So again, it is exactly similar to that case. You can get the acceleration component 0 and you can write those two equations. Okay. So let us see how we can do this. So basically, you should do it by yourself without looking at the video. First, make this figure. As you see, I have made this figure. 300 mm is written, so 0.3 meter I have written over here. This is your R, this angle is theta, this angle is obviously 90 degree, this is 30 degree, that is your pi by 6. So, this angle will be pi by 2, all the three 180 degree. So this is 90 degree already over. So this is pi by 2 minus theta plus 30, that is your pi by 6. So this is the angle. This angle is also equal to pi by 2 minus theta plus pi by 6. This is your r cap. So always you have to be careful what is your r cap. Basically, about which you are calculating r cap and theta cap and the fixed origin. So r cap and theta cap. This is your velocity vector. Acceleration vector is also along this direction. So there are a lot of equations, you can write it down. It is not that all the equations are necessary. So the first equation that you can write from this relation, and what will be that? R by sine 30, R by sine 30 is equal to 0.3 by 0.3 meter by sine of pi by 2 minus theta plus pi by 6. Whatever that is. So that is one relation that you get from this figure, geometrical figure. Then, second relation will be with the case of velocity. Alright? Velocity component. Velocity I know. So from the velocity component, basically I can find out. Now, I can write V of R. What is your V of R? Here it is V cos pi by 2 minus this. So I just write whatever it looks like. Theta plus pi by 2. Pi by 6. So V cos, and V is known to us actually, V is given to us. So VR is V cos this. That is equal to how much? Radial component of velocity is R dot. So that is one equation you have got. Second equations. Third equations you get is V of theta. V of theta will be V sine pi by 2 minus theta plus pi by 6, that is equal to r theta dot. That is your third equations. These two equations are relating to velocity. So this is from your geometry. The first one from your geometry. This is from your velocity. And 4th and 5th equations, you may not need all the equations, but you can verify one from the other. 4th equation is acceleration in the radial direction. That is your AR. AR is how much? 0. That is equal to R double dot minus R theta dot square. That is 0. And 5th is basically A theta is equal to 0. That is your 2 R dot theta dot plus R theta double dot. So these are the 5. These are from the acceleration actually. Acceleration. Okay. Now maybe you can calculate from these 3, or you can calculate from this, or you can calculate from here and then verify along with this line. So basically from these equations you can calculate all these quantities, whatever is asked for, and find out the numerical value. I don't have the answer because the book has not given the answer. But there are 2 important concepts that is here. One is this is a constrained motion, and you have to find out using the geometry the relation between r and theta. Be careful what is your r. That is the first thing. The second thing is, so maybe first is the geometry. I should write first is the geometry, and second point is velocity is constant. Velocity is constant and in a straight line. Velocity is constant in a straight line. From there we take the components and we get equations. From there we calculate velocity, again take components, then again we get equations. So this is a very important concept. In your assignment, there is one question which is question number I hope 7, and there is a rocket. I think there is a rocket again going in a straight line and with a constant velocity. So there also exactly similar kind of concept. So basically every question right from the first, second, third, fourth, fifth teaches us something. See, try to solve the problem and see what is the thing that you learn from each question. Okay, what is the concept that you learn? It is not the calculation or the algebra which is important, it is a concept behind the question is important. So every question, as you see, has an important concept. Try to learn that. Then try to solve the problems in an assignment. I hope you should not have any problem. Write down in brief every problem, the concept behind it, and the problem in short. And then try to revise it, think about it. You will see that you should be able to solve any problem in the examination. So this is all about the polar coordinates. Mostly it is the polar coordinates in we calculate velocity and acceleration. And there are something more we are not going to do too much. And the next chapter, what we will do, that we will be using these relations, that is velocity and acceleration, in with forces. So basically that is your Newton's laws. So Newton's laws in polar coordinates. So next chapter we will take up some problems and mostly problems and see that how we can solve some very important questions in Newton's laws using this basically polar coordinates. So that is all for today, and thank you very much. Wish you all the best.